Hi, I'm going to be walking through question 10 of round 2 of the Maths Teams Olympiad. This question was a challenge question for a reason. It was extremely hard, and at first glance, you'll say this is Fermat's last theorem, which was an unsolved problem for hundreds and hundreds of years until Weil solved it in the 1990s/80s, I believe. But it's not Fermat's last theorem. It's very different. Otherwise, I wouldn't be putting Fermat's last theorem as a problem on here. It's different because on Fermat's last theorem, it stated that n will be greater than 2, and there is no bounds here. So, for that reason, it must be significant that in this problem, these bounds and the fact that n is greater than 1 is significant. So let's start off by showing some results. This question, before I start, requires like a chain of logical reasoning, which is hard to follow, so I'm going to try go slow and explain it all, and try not get lost myself, because this has taken a few tries, so it's not the simplest to explain. So x is going to be less than z. I hope you see why, because x plus y is supposedly equal to z, so x will be definitely less than z. This is a strict inequality, so this means equality cannot occur. So x is less than z is strict, and the same occurs for y. Like so. Y is less than z. If we now say x is less than z minus 1, this inequality no longer becomes strict. It allows equality. And y is less than or equal to z minus 1 is also non-strict anymore. This minus 1 just allows it to be equal. When it's like this, it's possible to get equality, but before it was strict. And then you take 1 away, it's no longer a strict inequality. So furthermore, we can raise both of these to the nth power, and because we know both of these are positive and they are greater than 0 and they're natural numbers, we know the equality will stay the same, it won't flip, and we can say the following thing. X minus 1 is less than or equal to z minus 1. And with that same logic, we can say y to the n is less than or equal to z minus 1 to the n. Nice. If we add these two equations together, we get the following result. X to the n plus y to the n is less than or equal to 2 times z minus 1 to the n. This isn't so useful. If we knew this thing here, for example, if we knew that this 2 to the z minus 1 was strictly less than z to the n, then we could prove this, because that would say z to the n is always going to be less than x to the n plus y to the n. But unfortunately, sorry, that's an n there. Unfortunately, this fact here is not true. So it's not going to be as easy as just finding a way to do it that way. When solving the problem originally, if you didn't know this was true, it may be a path to try prove this, but unfortunately that does not work. But it's interesting just to see it. And these two results here do become useful later on, so I'm going to keep them there for a reason. Now, well, we know that we've got this bound here, and it's different because Fermat's that we need to include this bound somewhere in this equation. So we can suppose that y is going to be less than equal to x, which is going to be less than equal to n. We're just assuming x is going to be greater than y. There is no reason why we do this. We're just assuming it for ease. They could be equal, but we're just assuming x is greater than y. From this, we can deduce the following fact. We can say that x to the n plus y to the n is going to be less than equal to x to the n plus x to the n. Equality occurs when x equals y. Otherwise, when x is greater than y, the right hand side is bigger because x is greater than y. So I hope that makes sense. And we can replace x to the n with this inequality up here. We know that from this inequality here, we know that, note, x to the n is less than equal to z minus 1 to the n. Therefore, you can replace x minus n with z minus 1 to the n in this equality, because z to the n minus 1 is greater than x to the n, it's not going to change it. So we can say the following thing: z minus 1 to the n plus x to the n. And this inequality stays true. This looks like a binomial expansion in z minus 1 to the n. If it was a binomial expansion in z minus 1 to the n, this next term would be the following: z minus 1 to the n plus n z minus 1 to the n minus 1, and so on and so on and so on. This following term here, n times z minus 1 to the n, can be found. So I don't know how you would think of that in an exam. This actually comes from the BMO. I don't know how somebody would think of that up, but people exist who can be this smart. But if you note that x to the n is strictly less than equal to n x to the n minus 1. I hope this comes clear. I'm going to quickly try show you how. If you divide, oh, you see, I'm just going to move this over here real quick, sorry. If you can take 1 over to the side of a factor, or it's able to see, if you start with this original equation, x is greater than n, equal to n, x is less than equal to the n, sorry, less than equal to n, and this comes from this bound we have here. If we multiply both sides of this inequality here by x to the n minus 1, we get x to the n is less than n x to the n minus 1. And now we know, because n x to the n minus 1 is greater than x to the n, we can now replace x to the n with this here. So let's do that. And we get the following: z minus 1 to the n plus n x to the n minus 1. If we think back and we look at this, we know that x is greater than z minus 1. So if we raise both of these to the n minus 1 power, we get the following. And multiplying both sides out by n, we get the following. So we now know this term here, which is the same as this term here, is less than this term here. So we can replace this. And now we've got this new inequality. If we look back to this binomial expansion here, oopsie, let's get rid of that, we can now see this is what we were looking for. We've got this binomial expansion and we know it's true. We've proved it's true. So we can try write this binomial expansion a bit more formally. This binomial expansion would be the following thing. It would be z minus 1 plus 1 to the nth power. And this is equal to z minus 1 to the n plus n, z minus 1 to the n minus 1, so on. And then on like the other side you'd have plus 1. Considering the left hand side is actually equal to z to the n, and these two terms are contained in it, plus a load of other terms, depending on n, z minus 1 to the n plus n z minus 1 to the n minus 1, all the way so on. We can tell from this that I hope this is clear and you don't need to prove it. It probably would be satisfactory to prove it, but I don't have enough time. Z minus 1 is less than equal to z to the n. Because z to the n is made of this plus a few other terms, it becomes clear that this will be less than z to the n. If that you have the cases where n is 2 or n is a low number, you may have to show that individually, but for n greater than 2, it's obvious that this is the case. And now we basically got it. We know this is less than z to the n, so we can just replace this here and say this is less than z to the n. And we've got the following inequality: x to the n plus y to the n is less than z to the n. This has no inequality, and it's strict. So with these bounds here, x to the n plus y to the n will always be less than z to the n. So inequality can never occur. Therefore, we've proven the original statement.